Hello, my name is Tannie Liverpool. Before we start, let me show you something. So this is a pot of boiling water, and hopefully you can see the steam rising from it. The glass of tap water, which I just got from this glass. See that as I move the glass, the water, of course, moves to fill the, to change its shape, to accommodate the shape of its container. And then, of course, here is some ice I got from the freezer just a couple of minutes ago. And again, this is what we see this solid object. These are all everyday objects that we all used to seeing, and I want to say something about them in the following. Let us reflect on what we've just seen. The three phases we just saw were made up of the same stuff, but they were quite different. Ice, the solid, had a fixed volume and fixed shape. Water, the liquid, had a fixed volume but could change the shape to fit its container, while steam, the gas, didn't have a fixed volume and expanded to fill whatever container it's in this case, the room. But we know that the water is made up of water molecules. So how do we explain how these different phases emerge? And when I say explain, I mean we need to precisely describe how these phases emerge. And in order to do that requires some mathematical analysis. So let's, to get started, develop some mathematical notions that we'll need. Now, let's consider what's happened to my weight since the beginning of lockdown. So let's say t equals to 0. Let's say time, t equals 0. That's the lockdown, end of March. I had some weight. I stayed home. Didn't do much, so my weight went up. Noticed that my weight went up. Started doing some exercise to keep myself fit. After a bit of exercise, regular exercise, my weight went down to close to what it was before. But then after time, my motivation lagged, and I wasn't doing as much exercise as I was doing at the beginning. So my weight slowly crept up over time. So today it's not as high as it was at my peak, but a bit higher than it was at the beginning of lockdown. So my weight, as it varies through time, is an example of a function. It has an input, time, and an output, my weight, which I call f. So the time t, we can call a variable. And I can show my weight as a function of time by some curve whose height above an axis, which is measuring time, measures my weight. So higher weight has higher height. So let's look at functions in a bit more detail. The rate of change of a function with a variable, i.e. how fast the function changes when you change the variable, is called the derivative. So when the function is increasing, the derivative is positive, and when it's decreasing, it's negative. And the derivative at a point is equal to the slope of a line touching and parallel to the curve at that point. Another operation one can make on a function is to integrate it. The integral of a function between two values of the variable a and b is the area under the curve defining the function. So we have our curve f of x, which defines the function. And then, of course, this area here is just the defined integral from a to b of the function. Those are things that we will need to be aware of. We can generalize the definition of a function to two variables. For example, we could measure my weight as a function of time and height from the ground. We know that at very large heights in space, I would be weightless. So so you could use one axis would be time, other axis would be height, and you would have some surface which defined my weight as a function of time and height. And sort of analogy, we can define an integral of the function over the two variables x and y as the volume under this surface. And these notions we can generalize to n variables. So we can have a function where the function has n inputs, called x1 to xn. Now let us get back to atoms and molecules. Okay. Since everything is made up of atoms and molecules, which I'm going to call particles, so you have atomic gases like helium, and then you have other molecular gases like steam, or even oxygen. So I'm going to just call them, whatever the things, individual elements are, I'm going to call them particles. So particles could be atoms or could be molecules, or could be something else. So since everything is made up of atoms and molecules, then the state of matter must be encoded in what the atoms and molecules are doing. That is, where they are, their positions, and how fast they are moving, their velocities. So this is a sort of a video here, a schematic of some bit of matter. This is looking very gas-like and looking and seeing what the molecules are doing. So let's denote the position of the particle I by Ri and the velocity of particle I as Vi. And the velocity is just the rate of change of position with time. So it's the derivative of the position. And we're going to have I going from 1 to n, where n is the number of particles. And now if you think about the amount of water that you have in a glass, that would have about 10 to the power 23 molecules of water. So that's 10 with 23 zeros. So that's a huge number of particles. Now, so each of these particles must obey the laws of physics. Here, we're going to Newton's laws. This basically which says that particles move in a constant velocity, move with a constant velocity, unless compelled to do so by an external force. And the rate of change of the velocity is proportional to the external force. So the derivative of the velocity is proportional to the force. So if higher forces leads to higher changes in velocity. Okay, so that's what the particles are doing. We have 10 to the power 23 of them, a huge number. So we know what the velocity is, but what is the force? How do we get what the force is between the particles? So let's look at the trajectory of a single particle. So that means its path in time. So we can have, it's a curve where the position of the point of the curve is the position of the particle at a time t. So it starts up at t equals to 0 and ends up at t equals to t. So it's going to move in a straight line, and then with a constant velocity, and then when it changes direction, it must be due to external forces. So if we took any of these particles in here and followed it directly, we would see that it would follow some curve. At some time t1, it has position r1 and it's moving with velocity v1, which is the tangent to the curve, and then at some later time t2, it's moving with the velocity t2, again denoted by which is directed along the tangent to the curve. So the question is, how do we decide how the particle changes direction? And that it must change direction because of forces. Okay, and forces come from interactions between the particles. So what kind of interactions do we have between particles, and how can the particles impose forces on each other? So the interaction between particles has some generic features. When two particles come very close together, they apply repulsive forces on each other. And when they are far apart, they don't affect each other. So when they're very far apart, they don't know about each other. So that's kind of always true. The reason why they repel each other when they're very close to each other is due to Pauli's exclusion principle of quantum mechanics, which says that you can't put stuff. We know you can't put, I can't put my one hand where the other hand is. And essentially the same thing is happening for our particles, our atoms or molecules. So we've got this repulsive force at short distances and they don't interact at large distances. So it's what happens in between that is really important. And that's what determines what phases form and under what conditions. For lots of particles, by this I mean atoms and molecules, there is a range of distances when the particles feel an attractive force. This is essentially what leads to the different phases. This can be encoded in a function, which we call the interaction potential, whose derivative gradient determines the force. A very popular model, potential, which is sort of semi-empirical, is the Leonard-Jones potential. So John Leonard-Jones was an applied mathematician. He was professor of theoretical physics at Bristol, where I teach. So we've got an interaction potential. Imagine you have two particles who are separated by some distance r1, 2. There's a potential which depends on the distance. And the potential has this form. And the potential is attractive because we can tell whether the potential is attractive by looking at the force, which is the derivative of the potential. It's minus du by dr. And so clearly the gradient of the curve is negative here. So the force is positive, so it's pushing it away. And the gradient is positive for this region, so the force is negative. So there's an attractive force. And this attractive force is what is going to lead to the existence of phases. So we have the forces. So we now have a well-posed problem. We could write down some equations, and we know how to solve equations like that. But it is computationally intractable. we have 10 to the power 23 equations, one with 23 zeros. And this is billions and billions and billions of times more complicated than the best computer can ever solve today. So basically, we have no hope of solving these equations in any meaningful way, just because there's too many of them. And plus, there's too much information. We don't want to know what every single particle is doing. We want to know why is it that you have liquids and solids and gases. So the way to solve this problem is to use statistical mechanics. And in order to do that, let's try to be a little bit more concrete and think about the material we have. So let's consider a fixed amount of this material, e.g. a glass of water on a table. So it's not moving, it's sitting on the table. So we know then that the system is stationary, it's not moving, but the particles which make up the thing might be moving. Well, so let's allow them to move. And therefore, if they're moving, it must be moving in such a way as so that the glass doesn't move. So how can we think about that? Okay, so we're going to talk about this stationary piece of material like water or ice as, since it's not moving, we're going to call that thing a system at equilibrium. So the particles may be moving, but the system is stationary. So in order to solve this problem, we're going to have to use probability and statistics. So we need to do a little bit of a mathematical detour to develop some simple mathematical notions about probabilities. So imagine that you have a dice, normal dice, and let's say you make a large number, n throws of that dice. And you count the number of times you get 1, number of times you get 2, number of times you get 3, number of times you get 4, number of times you get 5, number of times you get 6. Call them n1 to n6. Clearly, if you add all the numbers, you're going to get n, because you've got total number of throws, and that's it. So we can define the probability of throwing a 1 is just the n1, the number of times you throw a 1 divided by the total number. The probability of getting I is just ni divided by the total number. And clearly, once we've defined probabilities, if we add the probabilities, we're just going to, that's the same as adding n over n, and that's 1. So we have this general rule, the sum of probabilities must equal 1. And of course, for an unbiased dice, we know that where all the numbers are equally likely, then the probability of getting any of those is just 1 over 6. Furthermore, we can get any average quantity regarding the dice from that probability. Now, the average score is going to be between 3 and 4, right? Because that's the middle of so it's 3.5. And in fact, we can get average score by just writing probability of getting 1 plus twice probability of getting 2, 3 probability of getting 3, and so on. So it's just the sum from 1 to 6 of I, the score, times the probability of getting that score, and we'll get 3.5. So using probabilities, averaging over probabilities, we can get, that will tell us how likely any scenario is, and will tell us what is the most likely scenario, or what is the most average, or what is the average of what one obtains. So we're now going to use this idea of probabilities to look at our molecules moving in the gas, or liquid, or solid. So the key idea of statistical mechanics at equilibrium is, rather than following the essentially uncountable number of particles n to the power 10 to the power 23, 1 with 23 zeros, we focus on their average behavior. And so for this, we need to get the probability of finding the particles with particular positions and velocities. So we can denote the probability of finding particle 1 with position r1 and velocity v1, and particle 2 with position r2 and velocity v2, and so on. This is a rather complicated object. It's a function of many variables. And let's be a bit more precise. Let's think about having n particles in a volume V. So we can define a density, which is just the number of particles divided by the volume. Now, since this is a probability, we know that if we sum over all the possible positions, we're going to get 1. So that's given that sort of an integral over these variables. That gives us 1. So the question is, if we can get the probability, then we can calculate averages of this gas, and that will tell us how this material will behave. And Boltzmann and others have given a prescription to how to calculate this probability for systems which are not moving. And in fact, the key idea is that the probability depends only on the total energy of the particles. It doesn't depend on precisely what the particles are doing. And this total energy remains constant, at least on average. So once we have that, then we can now calculate averages, and we can calculate the properties of this material. And one can do this. And of course, there's a fair bit of technical stuff in doing it, but it can be summarized in the relatively simple way. First, the temperature of stuff is related to the velocity of the particles. It's in fact the velocity squared. The higher the velocities of the higher the speed of the particles, the higher the temperature. And essentially what we find is that at high temperatures and low densities, now we can increase the density by increasing the pressure. So that means at high temperatures and low pressures, we have a gas, and that's this phase here. And at intermediate temperatures and pressures, we have a liquid. So that's it, you see. So we have the free surface there, and we have the liquid molecules there. So they kind of stay sort of stuck together. And then at high pressures and low temperatures, we have a solid. And what you see with a solid is that the particles are fluctuating about they have in a subregular array, and they're fluctuating about the regular arrays. And we can identify the boundaries between the phases and the transitions of one phase to another, which is sometimes sudden and sometimes smooth. And in fact, changing the potential between the particles will change the positions of the boundaries. And the details, of course, of how this attractive range of forces leads to the phases, of course, is subtle and requires lots of lovely maths, but effectively speaking, this is a framework that works. And essentially what we see is the emergence of collective behavior, liquid, solid, gas, from the particles and the interactions. And it's completely clear how this works. So this is very successful framework. So now let's look at some systems in which such a framework does not work. So these are two videos. One video is a video of a flock of starlings, which is going to go a dance. It's called a murmuration. And the second video is the first step in the development of the embryo of a fruit fly. And you can sort of see, this is called gastrulation. And you can sort of see the fruit fly developing this body plan being developed. So here is a couple of other videos. The first one was the first one on the left. This one was a cell crawling. So these are skin cells invading into a new region. And this third one here is a colony of swimming bacteria. Okay. So in all these systems, like our phases of matter, we have many interacting entities, but they're not stationary. The flock was moving, it's going somewhere, it was moving around. So if we define equilibrium as being something that's stationary, these things are not at equilibrium. So they're showing some collective behavior, they're moving together in some coordinated way, but they're not at equilibrium. And so we need a framework to describe them. And we want to develop a statistical mechanics to describe them. And the search is on to find one, and it's an incomplete search. And of course, there is sort of one big question is because what makes these systems different is that there's a source of energy, and because they're living, which is constantly being pumped into the system. And the question is, how is the collective behavior linked to the way the energy enters? And a key step to us understanding that is to look at simplified, possibly man-made systems with some of these features. And I'm going to take an example of an experimental setup, first studied by my friend Denis Barthelot from Lyon in France. So he's got small plexiglass spheres in a chamber surrounded by conducting liquid between two electrodes, connected to an electricity supply. The beads sediment to the bottom, and at a big enough, when a big enough electric field is applied, they start rolling along the bottom in a random direction. And then they form sort of synthetic flux. So you can sort of see this. Each of these dots is one of these particles, and you can sort of see them going around. So they're not stationary, they're moving. So this is a kind of synthetic flock which is swarming inside this racetrack. And essentially, the issue is that this happens only above the critical field. So a similar setup is now running in Bristol by some of my colleagues in physics and chemistry. So that's Abraham, Jerome, and Paddy. And what we'd like to do is to study the phase behavior of this system. So this is an experimental image, which has been colored and the color is just telling us how locally crystalline or solid-like the particles are. And blue is more solid-like and red is more fluid-like. So the left-hand video is showing what happens when the electric field is increased. At low fields, we have a stationary crystal or solid, And then as the field was increased, you can see this crystal starts to move, and then it eventually dissolves and forms a flock, a gas-like flock. So that's what happens as you increase the field. So on the right hand, we have what's happening at low fields. So we're seeing that at very low fields, it just forms a crystal similar to the solid phase we just discussed before. So let's look a little bit more closely at this, what happens when you increase the field. What you see is that we see amoeba-like moving clusters, splitting and coalescing. And this is a phase that you would never see such a phase in a normal material. You would have a liquid, solid, or gas. So this is not a liquid, it's not a solid, it's not a gas. What is it? So in order to describe this, we need a new framework, a framework that works for non-equilibrium systems which are not stationary. And a number of things we need. We need, because we have a large number of variables like before, so a dynamical description is not possible, it's computationally intractable. So we need a statistical description. So we need some way to get the probability, but it's not stationary. So we need to get this new framework which allows us to describe these complicated systems which are being driven energetically. This is an area of active research. I have a paper this year which says something about it. Other people have ideas about it. It's not done. This is a work in progress. See my paper from early this year. But in any case, as on our way to developing this new theory, a very useful way is to develop computer simulations of numerical models, which will, if they look like the experiments, will give us insights into what the ingredients we need for this new theory that is yet to develop. So on the left-hand side, we have some simulations done by my former postdoc research assistant, Majid. And he has done some numerical simulations, which seems to capture some of this amoeba phase, which is not seen in normal materials. So these types of simulations are going to be an important part of our final understanding of this new statistical mechanics for non-equilibrium systems. So I guess I kind of say here that we're moving towards a classification of the phases of this system. And if you want, as we increase the field, we have crystallized, something that looks like a solid. We go to this new amoeba phase, which is something that you would never see in a normal material like water. Have something that looks like a gas phase, but it's not a gas like steam, but this flocking gas where the particles seem to all flock together. And I'd even have, there's even more interesting stuff, which I'm not going to talk about. So enough about research. Now want to say something about, a few words about my trajectory. Highlighting some institutions where I could be found at some relevant moment in time. So I'm going to start at birth and not at conception. One of the beauties of time transition invariance is that you can choose your initial point. So T equals to 0, Royal Free Hospital in London. 5 years. I was at college school, FBC College School in Freetown, Sierra Leone. 10 years, I was at Baptist High School in Jos, Nigeria. 15 years, I was at the Blue Coat School in Wavertree in Liverpool. 20 years, I was to be found at Trinity Hall in Cambridge. Around 25, I was moving around a fair bit. I had a very high temperature at that time, you could say. And I could be found consecutively at the University of Cologne, at the Max Planck Institute in Mainz, and the SPCI in Paris, in France. Cologne and Mainz are in Germany. At 30, I was to be found at the Blackett Laboratory at Imperial College. At 35, at the School of Maths in Leeds. And at 40 and 45, at the School of Maths in Bristol, where I still am. It's been an interesting journey. Thanks.